Okay, so hello, I'm HYL, and today we'll talk about this paper, conformal prediction using decision trees. Yeah, it is it is come from this paper. Yeah, if you have interest, you can just read this paper. Yeah, and today I will just talk about the content of this paper. So of course we have the introduction and we have two backgrounds. One is conformal prediction and another one is decision trees. And next we'll talk about our methods and settings in this experiment. And finally we'll talk some experiment results. So I will try to explain this paper's content and find a relationship and some points I can make in my future work. Yeah, even if this paper focus on the classification case, because my research is focused on the regression case, but I think there's something are similar. So let's try it out. So in this paper, you have two common backgrounds. One is the conformal prediction, and the other one is decision trees. And we'll talk about conformal prediction first. Yeah. Okay. So this one will, this will be better. Okay, so about conformal prediction, we have talked about many times, but we still have to review it. So the central component of the conformal prediction framework is the nonconformity function, which gives a score to each instance and a class label player. And when classifying a novel instance, scores are calculated for all possible class labels, and these scores are compared to scores obtained from the instance from known labels. And when the corresponding conformity value is lower than a significant level, and they are excluded. And for each instance to be classified, the conformal prediction framework outputs a set of predictions, which may contain one, several, or no class labels. So, so this is the original formulation. This assumes the example to be classified has to be included in a celebration set, thus requiring recalculation for all nonconformity scores relative to each test example. However, the inductive setting has more efficiency, so it requires to split two proper training sets and celebration sets, and which are used to train the model and calculate the nonconformity scores. And here are steps to show the inductive settings. So first, we assume the conformity function C. This is defined relative to trained predictive model M. It's right like C and x line C is equals to FCMX. Yeah. And the x line is the vector of feature values, and C is the class label. And M line X returns to the class probability distribution predicted by the model. And the function F returns to the score calculated from the chosen class label and the predicted class distribution. Okay, so the p-value for the example x line and the class label C is calculated in the following way. That will be absolute value of S, which is the CS is smaller or equal to C x line C, and the denominator will be absolute value of S, and the S will be celebration set. Yeah. So the prediction for the example x line, where C1 to Cn are the possible class labels, which will be P x line sigma, which is C. C belongs to C1 to Cn, and and the P will be larger than sigma, and the sigma is chosen significant level. Okay, so the other background knowledge will be decision trees. Yeah, so the probability of techniques for learning decision trees can be explained by their ability to produce transparent yet fairly accurate models. And the generation of the decision tree will be recursively by splitting the data sets on the independent variable. So here are the general steps. So the first one, for each possible split is evaluated by calculating the resulting probability gain. If it was to be used to divide the data set D into the new subsets D1 to Dn, and the probability gain, the triangle is defined the following: ID minus the sum of PDI times IDI. And I is an imperative measure of the given node, and PDI is a proportion D that is placed in DI. And the split resulting in the highest probability gain is selected, and the procedure is then repeated recursively for each subset is split. Yeah. So different decision tree algorithms apply different imperative measures, such as entropy and Gini index. So although the normal operation of a decision tree is to predict the class label based on an input vector, decision trees can also be used to produce class membership probabilities. So here are three methods to obtain a class probability. So the first one is relative frequency. So this is the proportion of training instance corresponding to a specific class in a specific leaf where a test instance falls. So the probability estimate PICJ based on the relative frequencies is defined as PICJ will be equal to Gij divided by the sum of Gik, where so Gij is the number of instances belongs to class J that falls in the same leaf as instance I, and the C is number of classes. And there is another two methods. One is Laplace estimate, and the other one is M estimate. And the Laplace estimate and M estimates are a smoothing technique. So the main reason for using a smoothing technique is that the basic relative frequency estimate does not consider the number of training instances reaching a specific leaf. So PCJ is either assumed to be uniform, that is P equals to 1 divided by C, or estimated from the training distribution. So in uniform case, the Laplace correction is a special case of the M estimate with M equals to C. Okay, so this is our background knowledge of this paper. So so next part is the methods and experiment settings. So the overall purpose of this study is to evaluate different algorithmic choices for decision trees uses as conformal prediction. So there's outline steps for this one. So the first, we have to demonstrate the conformal prediction framework using decision trees that all trained with identical settings with several different settings are evaluated. So that we can include other experiment where standard ICP is compared to cross conformal prediction. And also here is some outline steps of CCP. Yeah, this CCP is the steps is similar to standard internal cross validation. So the first one is the available training data is divided to several folds, typically 5 or 10. So in this paper, it used 5 folds. And the model, here's decision tree. It is built from all but one of the folds, which is instead uses as the celebration sets. So we know that this procedure is repeated, so all folds are used as the celebration sets once. So the result is 5 conformal prediction, each having a separate celebration set. So the resulting p-value is found by averaging the 5 individual p-values. So note that CCP is found to be slightly more efficient than standard ICP. Okay, so the next part we're talking about is the experiment settings. Yeah. So in this experiment, all experimentation was performed in MATLAB and using the decision trees as implement in statistics toolbox. So in the following experiment, they compare different variables in the experiment. Yeah. So the first thing they will be compared is the Gini index and the entropy. And the second one is whether the pruning parameter is applied. Yeah, so they have two results. One is they will compare two things. One is they have pruning parameter, and the other is they didn't put the pruning parameter. Yeah, the pruning parameter, that means the optimize of the pruning based on internal cross validation. And also, there are 3 different ways of calculating the probability estimates. Just as I mentioned before, relative frequency, Laplace estimate, and M estimate. And the last, they have compared the ICP and CCP to conformal methods. Yeah, and also they have 4 measures here. One is 1C. 1C means the proportion of prediction that include just one single class. And another is multi-C. Multi-C is the proportion of prediction consists of more than one class label. 0C is the proportion of prediction consists of no class labels at all. Average C is the average number of class labels in the predictions. Yeah. So if you understand for these experiment settings, so we can just go on and discuss the results of the experiment. Okay, so the next part is the results. The experiment results, they have the 5 parts. Yeah, 5 parts. And the first part of the results, they demonstrate the behavior of conformal predictors. So here, the decision trees used for this demonstration were induced using a Gini split situation and no pruning. Okay, so they get a few outcomes. So the first one, for all data sets and significant levels, the error rate is very close to significant level. And also, when multi-C decrease and 1C increase as a significant level increase. Yeah, that is intuitive, right? So once there's no multiple prediction, the number of empty predictions start to rise. Yeah. Okay, so this is the first part of the experiment. So if you want to you want to understand more about this experiment, you can just go to see the paper. Yeah. Okay, so the next one, it shows the accuracies and size of underlying models. So they compare two split criteria, which is Gini index and entropy, and whether pruning or not. So for the pruning case, it used one of the smoothing techniques. And also for an unpruning case, it used M estimate in this part of the experiment. So in this experiment, we can understand these like hot cases have more coverage. Yeah, have more coverage. So of course, the pruned models in general are more accurate than the unpruned. Yeah, because the pruned models, they just optimize the pruning based on internal cross validation. So the prim models actually have a better coverage. And using a prim in a Gini split situation did result in significant higher accuracy compared to both sets of using unpruned trees. And also, the comparing model size presents us the total number of the nodes. The unpruned trees are of course significantly larger because the pruned trees is more accurately, so they relatively don't need more numbers of the nodes. Yeah. Okay. So the third experiment it shows the efficiency with different probability estimates and whether pruning or not. So we can understand this part as which case has the best average length. And here the average length is the number of the labels. So if you have more labels, the average length is larger. So and it is not efficiency, right? Okay, so in this part they have four different subcases. So the first one with using Gini and measuring by FC. So the best choice is obviously to use unpruned trees with either Laplace or M estimates correction. And the second best group is pruned trees using smoothing. And the second one, if we change the measure to 1C, so from average C to 1C. So the best tree is still the unpruned trees with smooth cases, then followed by the pruned trees with smooth cases. So, and the worst option with unpruned and unsmooth trees being the least efficient choice overall. So this is a similar result with the first one, right? Also, if we change the situation to entropy, the result is similar to the result of Gini. Yeah. So if we use the unpruned trees and M estimate smoothing is almost always significantly more efficient than all other setups, except unpruned trees smoothed by Laplace correction, because the unpruned M estimates and unpruned Laplace correction, both of them are the smooth cases. So the both smooth cases are similar for each other. Yeah. So we can see that the unpruned trees is more efficiency. This is because the pruned case have the more you have more you have a higher coverage. So the higher coverage, so if relatively you have more, the average length will become larger. So this is you will not too hard to understand why the unpruned trees will be more efficient. Yeah. So the fourth part of the experiment is the precision. That means in the settings, the proportion of removed labels that are incorrect. So we just found that. So we found that the most efficient setups is unpruned and smooth trees also have the highest precision. Yeah, that is of course. And the last experiment, it compares the standard ICP and CCP. So more precisely, it compares between the best ICP using non-pruning and M estimate and each case in CCP. So the ICP is often the most efficient setup, outperforming all CCP variants. So also we can find for each cases of the CCP, using no pruning and smoothing is the best option. Yeah, there's a similar result with ICP. So so therefore, from the experiment, the author says it is obvious that there is no need to sacrifice the interpretability of the single tree to produce more efficient conformal predictors through CCP. Yeah, so that means the ICP is good enough. We don't need to use the CCP. So also Alright, so just I said before, the paper the paper mentioned the paper mentioned the paper mentioned in the last part. It says the reason of the smoothing and avoidance of pruning results is more efficient prediction. It can be explained by the fact that pruning leads to fewer nodes since all celebration examples that will fall into the same nodes and have the same class label will obtain the same score. Yeah, so because the pruning you have the fewer nodes, so that means maybe you have because the nodes is smaller and they have the although they have a higher coverage, but they have a higher average length because the nodes becomes fewer. When we calculate it, there is something larger average length here. So this is because the pruning results have a poor efficiency. This is why. Okay, so this is the paper of the. This is my report for explain a conformal prediction using decision trees. Let me just tell again, if you have interest in this paper and if you want to understand more in the experiment results, you can just watch. You can just go to see the paper. Yeah, and this is my report and this is my report today and thank you everyone and see you next time. Bye.